Right now, as you watch this, someone is stealing your secrets. Not by breaking into your computer, not by guessing your password. Something much more patient than that. Governments, and we're talking about the big ones, are recording encrypted internet traffic. Billions of messages, bank transactions, classified documents, medical records, all of it encrypted, all of it unreadable, and all of it being carefully, quietly saved to massive data centers. They can't read any of it, not yet, but they're betting, and they're betting everything that someday soon they will. To understand why this matters, you need to understand what's holding the internet together right now. Every time you see that little padlock in your browser, every HTTPS connection, every bank login, every encrypted email, it's protected by a family of math problems that are really, really hard for computers to solve. The king of these problems is factoring. Here's how it works. Take two enormous prime numbers, multiply them together, easy. A pocket calculator could do it. Now take that product, this gigantic number, and figure out which two primes made it. For a classical computer with a large enough number, that's essentially impossible. There is no shortcut, no clever trick. You basically have to try dividing by every possible factor until one works. For RSA 2048, the standard key size used today, that would take a classical supercomputer longer than the age of the universe. Not figuratively, literally. The sun would burn out first. This is RSA encryption, published in 1977 by Ron Rivest, Adi Shamir, and Leonard Adelman at MIT. And it wasn't alone. Diffie-Hellman key exchange and later elliptic curve cryptography rely on similarly hard math problems. Together, these algorithms have been the foundation under every digital secret on Earth for almost 50 years. Your bank doesn't protect your money with a vault anymore. It protects it with a math problem no computer can solve. Then, in 1994, a mathematician at Bell Labs named Peter Shor ruined everything. Shor didn't build a quantum computer. He didn't have access to one. They barely existed. What he did was write an algorithm, a set of instructions for a machine that didn't exist yet, a blueprint for destruction. And what his algorithm proved was devastating. It said, "Give me a quantum computer with enough qubits, and I will factor any number you want." Not in billions of years, in hours. To understand why, you need to know what makes quantum computers different. A classical bit is either 0 or 1. A quantum bit, a qubit, can be both simultaneously in a state called superposition. When you have many qubits, the number of states you can represent grows exponentially. Instead of trying factors one at a time, it creates a superposition of all possible inputs simultaneously. Then it computes a function across every single one of those inputs at once. The result is a quantum state with a hidden pattern, the period of a modular exponentiation function. A quantum Fourier transform extracts that period from the interference pattern. And from the period, simple classical math gives you the factors. The math is beautiful and terrifying. Because if you can factor large numbers quickly, RSA is dead. Elliptic curve cryptography is dead. Diffie-Hellman is dead. Every public key crypto system protecting the internet, gone. With a single algorithm, Peter Shor wrote the death sentence for modern encryption. The only thing missing was the executioner. Now, here's the thing. Nobody has a quantum computer powerful enough to run Shor's algorithm on real encryption. Not yet, not even close. The largest number ever factored by a quantum computer using Shor's algorithm is 21. 3 times 7, that's it. That's the record. IBM's largest quantum processor, a chip called Condor, released in 2023, has about 1100 qubits. Sounds like a lot, right? To break RSA 2048, you need an estimated 4,000 logical qubits. But logical qubits require error correction, which means each logical qubit needs hundreds or thousands of physical qubits. The real number? Millions of physical qubits, with error rates orders of magnitude lower than anything we have today. We're talking about engineering a machine 1,000 times more precise than anything that currently exists. So why is everyone panicking? Because the gap is closing. Fast. In February 2026, researchers published a new architecture that could cut the hardware needed to break RSA 2048 by a factor of 10. Error correction techniques are improving year over year. Qubit counts are doubling. Expert consensus puts Q-Day, the day a quantum computer actually breaks real-world encryption, somewhere between 2030 and 2040. Some estimates say as early as 2028. We don't know the exact date, but the probability curve gets steeper every year. And here's the part that should keep you up at night. It doesn't matter when Q-Day arrives, because the damage is already being done. This is the strategy called harvest now, decrypt later, and intelligence agencies have been doing it for years. Think about what a spy agency does when it intercepts an encrypted message it can't read. In the old days, you'd throw it away, useless. But storage is cheap now, absurdly cheap. So you keep it, you keep everything. And in 2021, Booz Allen Hamilton, one of the largest defense contractors in the world, published a report with a blunt title about Chinese threats in the quantum era. The report warned that China may already be collecting encrypted American government data, diplomatic cables, defense communications, trade negotiations, intelligence reports, all copied, all stored, all waiting for the day a quantum computer can crack them open. The NSA acknowledged the threat directly in their 2022 CNSA 2.0 advisory. And it's not just the United States. Every government with sensitive data, every military alliance, every trade negotiation, every intelligence relationship is potentially compromised. Not today, but retroactively, because a classified document encrypted in 2026 might have a secrecy shelf life of 30 years. But if an adversary copies the ciphertext today and decrypts it in 2035, the secrets inside could still be devastating. Military positions, intelligence sources, nuclear capabilities, the names of covert operatives, weapons system specifications. The encryption isn't broken yet, but the theft has already happened. The vault is full, and the thieves are just waiting for the key. You can't see the breach because there's nothing to see. No alarms, no corrupted files, no ransom notes, just silence and patience. But here's where the story turns, because the people who build encryption, the mathematicians and cryptographers who defend the internet, they saw this coming. In 2016, the National Institute of Standards and Technology launched the most ambitious cryptography competition in history. The mission: find new math. Math that even a quantum computer can't break. 82 teams from around the world submitted algorithms. Universities, government labs, private companies. For 8 years, the world's best cryptanalysts tried to destroy every single one. They poked, prodded, and attacked each submission. Round after round, algorithms fell. By 2020, only 7 finalists remained. And then, on August 13th, 2024, NIST published the winners. 3 new standards that will replace RSA and protect every secret on the post-quantum internet. So, what is this new math? What did the cryptographers find that even a quantum computer can't break? The star of the show is called lattice-based cryptography, and the best way to understand it is with an analogy. Imagine a perfectly regular grid of dots, like graph paper, stretching out in every direction. In 2 dimensions, that's easy to picture. You could close your eyes and point to a dot. Now, stretch that grid into 3 dimensions. Still manageable. Now imagine that grid in 500 dimensions. You can't picture it. Nobody can. No human being can visualize 500 dimensions. But mathematicians can describe it perfectly. They can define every point, every distance, every relationship in that space with precision. Now, here's the game. I pick a point on this 500 dimensional grid. I add a tiny bit of random noise to each coordinate, just enough to push my point slightly off the nearest grid intersection. Then I give you the noisy point and ask, which grid point was I closest to? In 2 dimensions, that's trivial. You look at it and point. A computer solves it instantly. In 500 dimensions, the number of nearby candidates explodes. The search space becomes unfathomably large. Even a quantum computer chokes on it. There's no equivalent of Shor's algorithm for lattice problems. No known shortcut. No quantum trick. This is the learning with errors problem, LWE for short. And it's the mathematical bedrock of ml-kem, the algorithm selected by NIST to replace RSA as the world's primary key exchange mechanism. The beauty of it is that the encryption and decryption operations are simple. Just matrix multiplications with noise, but reversing the process without the secret key means solving a problem that neither classical nor quantum computers can crack. NIST didn't just publish one algorithm, they published three. ml-kem, that's the lattice-based key exchange. When your browser connects to a bank, this is what will protect the handshake. It replaces RSA and Diffie-Hellman for establishing shared secrets. ML-DSA, also lattice-based, handles digital signatures. Every software update, every certificate, every verified document. This is dilithium. And then there's the backup, SLH-DSA, based entirely on hash functions. No lattices, no exotic math, just hashing. It's slower and the signatures are larger, but it relies on the most battle-tested primitive in all of cryptography. If lattice math somehow falls, and nobody expects it to, hash-based signatures are the last line of defense. And here's the twist that most people don't know. This isn't theoretical anymore. It's not a white paper sitting on a shelf waiting for someone to implement it. The new encryption is already deployed on your phone right now. In February 2024, Apple did something extraordinary. They rebuilt iMessage encryption from the ground up. Their new protocol, PQ3, uses hybrid encryption. That means every iMessage is protected by both classical elliptic curve cryptography and post-quantum Kyber simultaneously. If the classical layer breaks, the quantum layer holds. If somehow the quantum layer has an undiscovered flaw, the classical layer still protects you. Belt and suspenders. Apple called it level 3 security, the highest level of any messaging protocol in the world. They claimed it surpasses every other messaging app on Earth, including Signal. Signal wasn't far behind. In September 2024, they deployed their own post-quantum protocol called PQXDH. Google Chrome started using hybrid Kyber for TLS connections in Chrome 124. That means every time you visit a website in Chrome, there's a post-quantum component protecting the handshake. And Cloudflare, which handles a massive share of global web traffic, reports that post-quantum encryption is now live across their entire network. The transition has already begun. Billions of devices, trillions of connections, and most people haven't noticed a thing. That's the sign of good cryptography. When it works, you never see it. But don't celebrate yet, because here's the ugly truth about the transition. Changing the encryption that protects the internet is not like updating an app. It's like replacing the foundation of a building while everyone is still living inside. Every server, every IoT device, every smart meter, every satellite, every military communication system, every banking network, all of it needs to migrate. Organizations that design their systems to be crypto-agile, able to swap algorithms without rewriting everything, can do it in 2 to 3 years. But most organizations, they have cryptographic algorithms hard-coded into legacy systems that haven't been updated in a decade. For them, it's 4 to 6 years minimum. And many organizations don't even know where all their cryptography is. They can't migrate what they can't find. NIST has set the deadline. All quantum vulnerable algorithms will be deprecated by 2035. The G7 endorsed the same target. That gives us less than 10 years. The race is on. And the pressure is creating panic. In March 2026, a group called the Advanced Quantum Technologies Institute announced they had discovered a new algorithm called JVG. They claimed it could break RSA with fewer than 5,000 qubits in just 11 hours, a 1,000-fold improvement over previous estimates. The headlines were apocalyptic. Cybersecurity Apocalypse 2026, the end of encryption. Global media ran the story everywhere. It was debunked within days. The algorithm hasn't been peer-reviewed. The scientific community is deeply skeptical. The math doesn't hold up. But here's what's telling. The panic was real. The fear was instant, because everyone knows that one day someone will make this announcement and it won't be a false alarm. Let's go back to Shor's algorithm one more time, because understanding exactly how it works makes the threat visceral. Classical computers try to factor a number by testing possible divisors one at a time. It's like trying every key on a giant key ring. A quantum computer does something fundamentally different. It puts a quantum register into a superposition of all possible values simultaneously, then it computes a modular exponentiation function across all those values at once. The result is a quantum state that encodes a hidden pattern, the period of that function. The quantum Fourier transform extracts that period, and from the period, classical math gives you the factors. The whole thing takes polynomial time, not exponential, not billions of years, hours. Here's what I want you to take away from this. Post-quantum cryptography isn't some distant future problem. The harvest is happening now. The standards are published now. The only question is whether the rest of the world catches up before Q-Day arrives. Every day of delay is another day of encrypted data collected by adversaries who are patiently waiting. Every legacy system that hasn't migrated is a ticking time bomb. Every organization that hasn't inventoried its cryptography is flying blind. The mathematicians did their job. They found the new math. The standards bodies did their job. They published the standards. The tech giants did their job. They deployed first. Now it's everyone else's turn. In 1994, Peter Shor wrote an algorithm that sentenced the internet's encryption to death. It took 30 years, 82 submissions from around the world, 8 rounds of brutal cryptanalysis, and the combined effort of the planet's best mathematicians to find the pardon. The new math is here. The standards are published. The deployments have started. The question is whether the rest of the world catches up before Q-Day arrives, because somewhere, right now, in a data center you'll never see, a server is quietly copying everything you send, every message, every transaction, every secret, and it's very, very patient. If this was helpful, don't forget to hit the like button and subscribe if you want to see more videos like this. Thank you guys for watching.